Hello, this is video number 14. We still got just a little bit that we need to talk about with number systems. Even though it's just a little bit is a huge deal, we don't have any way yet to represent negative numbers. And if you're going to be a number system that's got to do math on a computer and everything, you better be able to represent negatives. So let's look at binary negatives. How do we represent negative number? Well, fortunately, that's almost trivial. That's just so easy. For these examples, I'm going to assume an old, well, I don't even know that there are any this old, an old 8-bit machine. Which, among other things, means the default size of a number is going to be 8 bits. It just makes it easier to work with. If we could figure it out for 8 bits, then we could do it for 16 bits or 32 or 64 or any number of bits. So this is just so that when we make up examples, we don't have to have a lot of bits in a row. Let's do this. Do this. Use the leftmost bit to represent the sign of the number. R-E-P-R-E-S-E-N-T. The sign, positive or negative, the sign of the number. There. That was easy. Let me do a couple of examples. Example. Positive 3. We know how to do positive 3. We've already done number conversions. That one's easy. On the place value, I keep saying stuff is easy. I need to stop that, huh? Positive 3 on an 8-bit number system would look like 0, 0, 0, 0, 0, 0, 1, 1, right? You can visualize the place value chart by now. I know you can. You've drawn so many of them and seen so many of them. That's a 1 and 2's place, a 1 and 1's place, and yes, when you add those up, you get 3. Now I'm going to make this a nice bold 0. I don't think there's any way to make a bit bold in a computer, but for the number representation's sake, that 0, I'm kind of splitting that off. This is now two different pieces of information stuck together in one number representation in the machine. The 0 means positive. The rest of the number is what goes on the place value chart. So this 0, I wouldn't technically put that on the place value chart. That doesn't mean add this much to the magnitude of your number anymore. It just means this is a positive number. Since that's positive 3, then negative 3. Negative 3 would be solid bold 1, which also is impossible on the machine. But that's what we're doing. We're splitting off the leftmost bit to represent nothing but the sign of the number. 1, 0, 0, 0, 0, 0, 1, 1. What could be simpler? Not a whole lot. This actually has a name. I'm going to write it in frightening red, but it's not really frightening. This is called the sine and magnitude number representation. I wonder who came up with that. Genius. Sine and magnitude. M-A-G-N-I-T-U-D-E. I'm a horrible speller. Sine and magnitude representation. Where the bold bit is the sign, 0 for positive, 1 for negative, and everything else is the magnitude. You slap on your handy dandy place value chart and add it up and away you go. Now then, now we can do addition with positives and negatives. Let's add these two up over here. I'll put that in parentheses so it doesn't look like I have two signs in a row. Positive 3 plus negative 3. Well, duh. I know that. That's goose egg 0. And I better put a little 10 down here just because I've got more than one number system running on the board here. Now let's add these up. 1 plus 1 in binary, that's 2, but you put a 0 and carry a 1. Old time's sake, a review of binary addition. 1 plus 1 plus 1, that's 3, but I put a 1 and carry a 1. 1 plus 0 plus 0. Finally an easy one. That's just 1. 0's all the way across. 0 plus 1 is 1. And this is binary, but Houston, we have a problem. If we're saying that this is our sign and magnitude representation, and that it is, that's sign and magnitude, so this is, when I add these up, I'll put a plus sign over here, shows how I got that. That is actually negative something. Negative, place value chart, 4 plus 2 is 6, negative 6. What's the problem? The problem is that 0 is not equal to negative 6. So even though this was really easy, and it was actually used, those old computers you see in old newsreels or whatever that have things that look like light bulbs, the tube computers, they use sign and magnitude representation. But here's the problem. Today is multicolor day, I guess. And I'll write it out as a problem. Problem! A big one for number systems. Arithmetic is not supported by sign and magnitude. Meaning arithmetic doesn't come up with the right answer if you're using sign and magnitude representations. Arithmetic, A-R-I-T-H-M-E-T-I-C. Arithmetic is not, double underline, supported by, and I'll abbreviate, we're on a first name basis, I'll call it sign and mag representation. And that's such a big deal, I'm going to put an exclamation point. For a number system that wants to be your number system on your computer, pick me, pick me. That's a big deal. You don't want a number system that doesn't support arithmetic. Now, of course, I've completely filled up the board, and I don't have any space to try to sneak up on a better way to do this. But before I erase all this, I'm going to drop a definition on you. Definition. The additive inverse, the A-D-D-I-T-I-V-E, inverse, I-N-V-E-R-S-E, the additive inverse of, that black marker is no good. We ask that you bear with us. The additive inverse of a number, that's oh so much better, of a number in it sounds frightening, but it's not. The additive inverse of a number n is the number you must add to n to get 0. Well, that seemed to just drop out of the sky, didn't it? It must have something to do with representing in negatives, but it might not be apparent yet. Let's see. The additive inverse of a number n is the number you must add to n to get 0. Oh darn, I really don't have room for an example. Oh wait, there's already an example. 3, look at this. Positive 3, the additive inverse is negative 3, because that's what you got to add to positive 3 to get 0. Oh wait, there's more. The additive inverse of negative 3 is positive 3. So it goes both ways. The additive inverse, notice I didn't say that it was positive number n. It could be negative number n. In base 10, it's fairly straightforward. You just flip the sign over here. You go from positive to negative or negative to positive, and boom, you've got two numbers you can add up and get 0. Now, think deep thoughts about that while I erase the board so that we can start all over again and filling it up. It's still binary negatives. We still don't have a good system to use here. Sign and magnitude. Bless your heart. You tried. You just couldn't do it. You can't do math. Can't do math. You can't be our number system. I said erase the board. I actually meant smear it. Now that I've smeared the board, let's try something else. Talk about sneaking up on stuff. I'm going to say that we're going to use a trick. Tricks are good. Always use a trick. Let's suppose that we have 1 And let's go in search of. I just use that because that's about the simplest well, it's the smallest binary number that's not 0 that we can even think about. That's positive 1. I'm not even going to elevate that to put its equivalent in decimal on the board. Positive 1. What could I possibly add to that to get 0? Yikes. You know, what we could try to do is, what could we try to do? Here's maybe that. Actually, no, I'm sorry. That's moving the wrong way. That's going to give us solid 1s. So much for that. Talk about backfiring. What did I do? How did I even get that bit pattern? All I did was flip them. If it was a 0, I put a 1. If it's a 1, I put a 0. But that went the wrong way. Now I'm going to ask you, here comes the trick. I'm going to ask you to imagine that you are some poor, starving computer science professor, but you have this old jalopy that has an odometer that's binary. Of course you do. You're a hopeless nerd. You've driven your car so many miles and the odometer reads solid 1s. You can't afford a new car, but good news for you. You only have to drive it 1 more mile. Watch what happens if you drive your binary odometer car 1 more mile. Watch this. I call it the ever-popular domino effect. 1 plus 1, that's 0. Carry a 1. Well, look here. 1 plus 1, that's also 0. Carry a 1, 0. Carry a 1. Rapidly, we see a pattern developing. And just like dominoes, let's come in for a landing over here. When I add 1 plus 1 gets 0, there is a carry over to the next column that, poof, falls off a cliff. We don't even see that. There's no room for that in the answer. We only have 8 bits to represent the number. But look what we did. We reset our binary odometer to solid 0s. Somehow or another, through all these contortions up here, I started with plain old 1. I wanted to get back to 0. I got back to 0, but good grief, look at all the pain and suffering we had to go through to get there. What did I do? Well, first of all, I flipped the bits. I started with solid 0s and a 1, and I flipped it so I got solid 1s and a 0. I'm going to call that stage 1. Flip the bits. That didn't bring me all the way around to 0. Actually, it looked like it took me much, much further away. Solid 1s here. Solid 1s. But if I have solid 1s, stage 2. Add 1. If I flip the bits and add 1, then the sum of all of these things, I actually did 2 additions. One was this plus the flip bits, and then I took the flip, add those 2 together and add 1 more. That brings me around to 0. So, stage 3, add up, get 0. That doesn't look like much of a trick. That looks just a bunch like a bunch of weird scribbling going on here. What's the deal? Well, actually, here's the deal. When we flip the bits and add 1, I'm going to label these things here. This I'm going to label number A. This is number B. 1 is number C. So I've got 3 numbers. I described that way wrong. Let me describe it this way. This is number letter A. This is number letter B. This is number letter C. Now, what on earth am I trying to get at here? Who knows? But it looks like I added A plus B first. Pull this down here and try to make it general. I took number A, which is what the 1 I started with. I added B and came up with the sum. This is A plus B right here. There, I got A plus B. What did I do with A plus B when I got it? I added C. When I add all three of those up, you know what? I'll label this as well, even though I didn't leave any room for it whatsoever. That little sliver right there was A plus B. We're still waiting for the trick, aren't we? It's on the way. Hold your horses. A plus B, I got A plus B. Add C. That got me back to goose egg 0. Now, here's the deal. If there is a mathematician in our studio audience, you will probably be nodding knowingly saying, you know what? Those parentheses, I could shift those around if I wanted to. It's called the Associative Principle. I think I'll do that just for fun. A plus B, if I add those first and add C and get 0, that's exactly the same result I'd get if I started with B plus C and added those up first. I'd still get 0. And I'd still make no sense whatsoever. And I'm still waiting for a trick. Here's the trick. In general, A, the number you start with, that's going to be that capital N that I spoke about what seems like a long time ago now when I was talking about additive inverses. Oh no, what do I have to add to N to get 0? I have to add B plus C. What was B? That was the flip bits. Flip the bits, you get B. What was C? That was 1 all by itself. This, ladies and gentlemen, that's negative N. I'm not even going to call it negative N. This could be negative. This is the additive inverse of N. There's the trick. We now have, in effect, a mathematical formula to calculate the additive inverse of any, not just one, any number we start off with. What, pray tell, is that formula? Flip the bits, get a different bit pattern, add 1. Now we've got flip the bits, add 1, whatever that turns out to be, is going to be what we have to add to N to get 0. That doesn't seem like a good trick. That seems awfully complicated. I'm afraid I might have complicated it unnecessarily. So if you've got all that written down, you can come back and look at it and maybe even watch that part of the video again later and nod knowingly, oh yeah, that's what he was trying to talk about. Let's try the trick in some other number. We had a problem with 3, didn't we? Let's try 3 again. Here's an example of our trick. Positive 3. Positive 3 looked like 0, 0, 0, 0, 0, 0, 1, 1. Ah, yes, I recall it well. Not really well, but I'm pretty sure that's what it was. Step 1, flip the bits. If I flip the bits on this one, I'll get, I should write that out. Step 1 is flip. There. Flip. Where it's a 0, put a 1. Where it's 1, put a 0. 1, 1, 1, 1, 1, 1, 0, 0. Done and, no, we're not done. That was only stage 1. Stage 2, add 1. There's flip. Now I got to do an addition. I take the flipped version and add 0, 0, 0, 0, 0, 0, 0, 1. Add 1 to whatever the flipped version of your original number is. Now what do we get? We get 1, 1, 1, 1, 1, 1, 0, 1. And I can't write a little 2 down here anymore, even though this is a binary representation. Here's the weird part. This does not fit on the place value chart anymore. This is now our representation of negative 3. That doesn't look like any negative 3. I'm going to say it's equal to negative 3 in base 10. How could I even check and make sure that that's a usable negative 3? Here's what the trick is. Why did we flip and add 1? What we're looking for is not a number we can slap on our handy dandy place value chart and figure out what the hey it is. We are looking for just the raw bit pattern we've got to add to what we know and love as positive 3 up here. Positive 3 equals that. And I am looking just for the bit pattern that I got to add to that to completely overload my binary odometer and reset the machine for these 8 bits back to 0. Let's try it. Positive 3. Positive 3 is 0, 0, 0, 0, 0, 0, 1, 1. Our new version of negative 3, let's try that out. It says it's, look at that, that doesn't look like 3 at all. That is purely just a bit pattern. 1, 1, 1, 1, 1, 1, 0, 1. Over here, add positive 3, negative 3. We're still going to get 0. Add these up. That color doesn't look very good. I want those to show up better. Wait a second. That's no better. Okay, back to black. None of these other colors are doing me any good. 3 is 0, 0, 0, 0, 0, 0, 1, 1. One moment, please. Negative 3, or so we claim, is 1, 1, 1, 1, 1, 1, 0, 1. Maybe I'm just afraid this won't work and I'm procrastinating. See how clever I am? Let's add those up. 1 plus 1, 0, carry 1. 1 plus 1, that's 0, carry 1. 1 plus 0 plus 1, that's 0, carry a 1. 1 plus 0 plus 1, look at, oops, not that. I carried in a 1, I add a 1, I get 2, but I put a 0 and carry a 1. Put a 0, carry a 1, 0, carry a 1, 0, carry a 1. 0, here comes a moment of truth. Put a 0 because there was a 1 carried into this column. 1 plus 1 is 2. Put a 0. Look what happens with the 1 that gets carried. It falls off the machine. There's no room to store that in my 8-bit number representation. So what I did was forcibly reset this back to 0 by, in effect, ending up with a number that was just a little bit too big to represent on the machine. Now, if that's not a trick, I don't know what is. We're forcing our binary odometer to run past all the numbers that it can represent. But we do that on purpose. That's why we're calling this negative 3. Why? Because it is the additive inverse bit pattern of 3. Concentrate on that until it makes sense. Why? Why? That's not on a place value chart. That doesn't make any sense at all. What could that possibly be? Well, if we add it to 3, it gives us 0. So we, as the designers of the machine, if we're the ones that are designing the machine and the machine language it uses and everything, we get to decide what these bit patterns represent. I now pronounce you to be negative 3. Why do you get to be negative 3? Because I add you to 3, I get 0. That just doesn't seem like that ought to work at all, but in fact, it does. Surprise, surprise. Let's try another one of those. Give me a number, any number. 19? Okay, let's try 19, base 10. And now I am going to put this, we no longer have to imagine it. Here comes our 8-bit, 1, 2, 3, 4, 5, 6, 7, 8. 8-bit place value chart. 1's place, 2, 4, 8, 16, 32, 64, 128, repair the 8, it looks feeble. There we go. Now starting on the left over here, going left to right, since this is an 8-bit pattern I want to end up with, I'm going to fill in every column whether there's anything there or not. There are not any 128s, that's a 0. No 64s, no 32s. Oh wait, there is a 16. 16, now we can do the subtraction in our imagination. 19 minus 16 is 3. There are no 8s in that. There are no 4s. There is a 2. There is a 1. There we go. This is positive 19. How can I represent negative 19? It's not as easy as splitting off this first bit and making that the sign bit anymore. To get the additive inverse, repeat after me. To get the additive inverse, the 2 steps are flip the bits, add 1. Here's flip. I would switch colors to make it more interesting, but I don't trust these other colors anymore. I'll flip as I copy them down here, and this will be step 1. Flip will be 1110, 1100, Double check and make sure I flipped correctly. 1110, 1100. It looks flipped to me. Step 2, add 1. Why are we doing this? What are we doing? We are forcibly generating a pattern, we hope, that we can add to 19 to reset us back to 0. That is our goal here. Flip the bits, that gets us, if you recall, that gets us almost there. Flip the bits, add those up, I'll get solid 1s. I need to add 1 more to actually completely reset the odometer. Well, look at that. This is purely by accident, but it's a happy accident. I don't have to carry anything. Every column is either a 1 or a 0. 1 plus 0 is 1, 0 plus 0 is 0. There's a 1 there, there's a 1 there, there's a 0 there, and 1, 1, 1. And I look at that and I think, yeah, that'll be it. That looks like negative 19. Look how confident I am. I'm even going to say that that equals negative 19. How can I check and see whether or not that's actually negative 19? I can try to find a marker that will actually write. Let's check and see. Check, please. Positive 19. 0001. 0011. And this monstrosity here that we're claiming is negative 19. Negative 19, maybe I'll put a question mark up here because I'm not sure. Are you negative 19 or not? 1110, 1101. Ideally, we will start up this ever popular domino effect again, and all these ones get carried and carried and carried until one falls off the edge, meaning it's going to look like 0. We've driven our old jalopy binary car until it flipped over odometer from solid 1s to solid 0s, just with 1 more. 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. And ladies and gentlemen, I think we're going to have 1 plus 1 is 0. I'll do this last column a little more deliberately here. 1 plus 1, there was a carry in of 1 you didn't see there. 1 plus 1 was 0, carry a 1. 1 plus 1 is 0, carry a 1. But there's no column to carry it over to, so it falls off the edge. You and I can see it hurtling to its death down here in the abyss, but the computer can't see this one at all. It's actually, we've generated a little case of an overflow. We've got a number that's too large to represent on the machine, but to the machine it looks like 0. So in fact, that is the representation of negative 19. Okay? You know, I still can't get rid of this urge. Here I go. Any questions? If you've got questions, bring them up during office hours. Oh, this number system has a name, which is a good thing, because this is the one that's actually used. Every computer now, ever since we got past those light bulb style computers, those fuse computers, tube computers, this is called 2's complement. Complement? Yeah, I guess that's right. 2's complement. I'm not sure why. Oh, you're looking lovely today. There's the complement. 2's complement representation. 2's complement representation means to get the additive inverse of a positive number, flip the bits and add 1. Oh, wait, I slipped a word in there that doesn't belong. I said to get the additive inverse of a positive number, flip the bits and add 1. Here's one more example. Well, I keep saying one more, just one more, just one more. Our algorithm, our recipe, our formula for getting the negative does not depend on it starting as positive or negative, either one. In other words, we are purely generating a bit pattern that is the additive inverse of another bit pattern, no matter what it starts out as. I've done only ones that we know up front what they are so that we could double check them. Look at this. 1, 1, 1, 1, 0, 1, 1, 0. And let's say that we know we are in the 2's complement number representation system. Couple of things here. This isn't officially sine and magnitude, but still, we can look at the very first bit. In 2's complement, the very first bit will be a 1 if it's a negative number. So we do know that this bit pattern is a negative number. We just don't know it's the negative of what. Honestly, I don't know. I just made up those zeros and ones. I know in 2's complement that will be viewed on the machine as a negative number, but I don't know negative what. What's a professor to do? How do I find out what that is? Question mark over here. Question mark base 10. What are you, you bit pattern? Well, here's where our 2 steps come in. Let me write it down here to make it a separate problem. Do the scratch work down here. 1 1 1 1 0 1 1 0. I still follow exactly the same 2 steps. One flip, because all I'm doing is looking for the bit pattern that I have to add back to this thing to get 0. To do that, I flip the bits. 0 0 0 0 1 0 0 1. And after I've done that, I need to do step 2, which is add 1 to that. I'll go ahead and do that while I've got the right color marker open. But that will be step 2. Step 2, add 1. When I add those up, I get, let's see, 1 plus 1 is 2, put a 0, carry a 1. That's as far as it goes. 1 plus 0 is 1, and the rest of it's easy. 0, 1, 0, 0, 0, 0. Now watch and be amazed, as I am, that this even works. That, since that has 0 as the leading bit, this is a positive number. Oh, wait, there's more. Not only is this a positive number, I can still slap my positive numbers on my handy-dandy place value chart up here. This one is 0, 0, 0, 0, 1, 0, 1, 0, and find out what the hey that number is. What the hey is it? Well, it's an 8 plus a 2. Oh, no. That's what happens when I use random patterns over here. The reason that's an oh, no is because this is 10. You know what? I'll make them bold. It looks like I got 2 in binary. 10 with a little subscript of 10. What a horrible coincidence. Yikes. I'll have to do another couple of these, I guess. Maybe not. Maybe 1. We'll see. But this, since this is positive 10 down here, and that's what I have to add to this original bit pattern to get 0, what that means is this is no longer a mystery. This is a 10 in base 10. Horrible, horrible coincidence. It looks like it's still in binary. It's not. Maybe if I circle it, it looks like it's in base 10. I said this was 10. I lied. That's negative 10. I know it's negative because it starts with a 1. What I can't do, let me review what just happened here. What a disaster. This was a random bit pattern I made up. It's 8 bits. I know it's a negative number in the 2's complement number system. What I don't know is what negative number it is. How do I find out? Well, I find out it's positive additive inverse. I flip the bits and add 1. When I do that, I get a bit pattern that is a positive number. Slap that on the place value chart, add up the place values. 8 plus 2, so unfortunately, equals 10, which still looks binary, but it's not. That's a 10. So if that, put on our logic hats, or maybe our tinfoil hats, one or the other, put on our logic hats, if that's positive 10, when I add it to my bit pattern and get 0, that means that this must have started off as negative 10. Maybe I'm over-explaining. Maybe that's the problem. I'm going to keep the place value chart, and we're going to do a math problem. You know what? I'm going to cut my losses on this. I'll leave the handy-dandy place value chart up there, and we'll do a math problem in the next one. I'll see you online.